Hello viewers, today we are going to look at triangles and its various kinds of centers. Mostly we will focus on the centers of triangles. We will see the different centers we have here. First, you all see 4 triangles. Almost all are similar until unless I differentiate them. Triangle ABC. Here in the first figure, AD, I am saying AD is a median. So, AD is a median here. Median is a line which bisects the opposite side, and median also divides the entire triangle into 2 equal areas. And if you look at the median, median divides the entire triangle into 2 equal areas, and the intersection point of medians, I call it as IP, that is intersection point. Intersection point of a medians is centroid. Now look at the second figure. Here AD, I call it as an angular bisector. In the second figure, AD is an angular bisector. The first figure, AD is median which divides the opposite side. Here it divides the angle. So these two angles are same, theta and theta. Here this is phi, this is phi. Intersection point of angular bisectors is in center. Now look at the third figure. Here AD is perpendicular to the base BC. BE is also perpendicular to AC. So you call it as an altitude. And the intersection point of altitudes is called orthocenter. In the last one, I do not call it as AD, but here this line is perpendicular to BC and it is dividing BC into 2 equal parts. So I call it perpendicular bisector. So here this is perpendicular bisector, and the intersection of perpendicular bisectors is called a circumcenter. First, medians, intersection. What is median? A line which divides the opposite side into 2 equal parts is a median. Now intersection point of medians is called centroid. Second one, the line which divides the angle into two equal angles is angular bisector, which is dividing the angle into 2 equal angles. Here AD is an angular bisector of angle A and BE is an angular bisector of angle B. Now the intersection point of 2 angular bisector, we call it as in center. And look at the third figure. The third one is perpendicular. AD is perpendicular to the base BC. So intersection point of these altitudes, we call it as an altitude. Intersection point of altitudes is orthocenter. Now in the fourth figure, here this line is perpendicular to the base BC and it is dividing the BC into 2 equal parts. We call it as a perpendicular bisector. Intersection point of perpendicular bisectors is circumcenter. First we look at how centroid appears in the different triangles. Suppose if I take an acute angle triangle, that point here is a centroid. In an acute angle triangle, centroid always stays inside. Even if you take it as an obtuse angle triangle, this is an obtuse angle triangle, it is also inside. If you take exactly a right angle triangle, in right angle triangle also centroid is always inside. So centroid for acute angle triangle and obtuse angle triangle and right angle triangle, it always inside. Now here these are 3 angular bisectors. Look at it, is called in center. The intersection point is in center. In center is always equidistant. In center is always equidistant from the sides. And here for an acute angle triangle or obtuse angle this is an obtuse angle triangle. In center stays inside. This is a right angle triangle. In center stays inside. Even if you take an acute angle triangle, all angles are acute angles. Here also it stays inside. So for all triangles it stays inside because it's an in center. And in center is equidistant from all its sides, not from vertices. It is equidistant from all its sides because you draw a circle inside. Now we look at orthocenters. Orthocenter is actually intersection point of perpendicular, as you see in the figure. Look at the perpendiculars here. If it is an obtuse angle triangle, orthocenter stays outside. If it is an acute angle triangle, it is coming inside. If I take exactly a right angle triangle, orthocenter is exactly at right vertex. If I take right angle at A, orthocenter stays at A. If I take the right angle at C, so orthocenter for right angle triangles is at right vertex. For an acute angle triangle it stays inside, for obtuse angle triangle it goes outside. So acute, obtuse, for a right angle triangle it is exactly at the right vertex. So even if I take the right vertex at B, orthocenter stays at right vertex. Acute inside. If I go for obtuse, it goes outside. Now we look at circumcenter. Circumcenter is an intersection point of perpendicular bisectors. For an acute angle triangle, it stays outside, as you see. For a right angle triangle, right vertex at A, but for a right angle triangle it is exactly the midpoint of hypotenuse. It is exactly the midpoint of hypotenuse. For obtuse, outside. Acute, midpoint of hypotenuse. If you go for acute, it is inside. Acute inside, obtuse outside. For a right angle triangle, it is exactly at the midpoint of hypotenuse. And if you look at this circumcenter, circumcenter is always equidistant from the vertices. Circumcenter is always equidistant from vertices. If I take right angle at C, suppose, it is exactly midpoint of AB, acute, obtuse. We will see all the three positions once again: acute, for obtuse, and for right angle triangle. First, go with centroid, in center, orthocenter, circumcenter. Acute, all the centers are inside. Obtuse, acute is always inside. Obtuse, centroid and in-center is always inside. Inside, inside. For centroid is always inside, whatever the kind of triangle it is inside. But when it comes to obtuse and orthocenter, orthocenter will be outside. Circumcenter is also outside. When it comes to right angle triangle, orthocenter is at right vertex. At right vertex. Now circumcenter is exactly midpoint of hypotenuse. So these are the positions of centroid, in-center, orthocenter, circumcenter with respect to acute, obtuse and right angle triangles. Medians, centroid. Take a triangle, draw the median A, B, C. D is a median. D is a midpoint of BC. Now here AD is a median of this triangle. AD, as we know, divides the triangle into two equal areas and as well as BC into two equal parts. If I take BE is also median, centroid, and this O, centroid divides median in the ratio of two is to 1. This is 2 is to 1. So centroid divides the median in the ratio 2 is to 1. We further look into it. I am taking all three medians here. Usually if you take a triangle, its bases are in the ratio 2 is to 3. You look at two shaded regions here, one is the ash color one and one is the pink color one. If I ask you ratio of their areas for both the triangles, let me name it triangle ABCD. Here triangle ABD I am taking it, I am dividing triangle ABD by using AC into two parts. Into two triangles, the first one is ABC and the second one is ACD. If you ask me the ratio of ABC and ACD, they are in the ratio 2 is to 3. Their area is also in the ratio 2 is to 3. Because for both the triangle ABC and ACD, for ABC and ACD heights are same. So areas will be in the ratio of their bases. So remember this, when both the triangles having the same height, areas will be in the ratio of their bases. Look at triangle ABC. All this AD, BE and CF are medians. G is a centroid. Centroid divides the entire triangle. Centroid divides the median in the ratio 2 is to 1 and median divides the triangle into two halves. So first one, I am just shading this region. Look at triangle ADC. Look at the triangle ADC. Triangle ADC is exactly half of ABC. Triangle ADC is half of area of triangle ABC. And you also look at only the pink part. And the hash color part. We know that the centroid divides the median in the ratio 2 is to 1. Therefore, this area is one part. Therefore, this entire hash color one is two parts. Therefore, I am taking it as 2x. This hash color area is 2x. Specifically naming it AGC is 2x. But look at what is GE. GE is a median for the triangle AGC. GE divides the triangle AGC into two equal parts, which means it is x. The 2x is divided into x and x. So what you get from this? All the 6, suppose all the 6 triangles you see here will have equal areas, whereas AD, BE and CF are medians. So, these 3 medians divide the triangle into 6 parts. All these 6 parts are having equal areas. Now, see here, I will take the triangle BGC. Area of triangle BGC is 1/3 of area of triangle ABC. Now, take the triangle AFE. Now, here E and F are midpoints. Therefore, triangle AFE this is a midpoint. According to midpoint theorem, we know it is line joining two midpoints is half of the third one. Therefore, sides ratio is 1:2. Areas ratio will be, if it is 1, the entire triangle becomes 4. So, we know if sides ratio is 1, because they become similar triangles, if sides ratio is 1:2, then areas ratio will be 1:4. Therefore, triangle AFE is 1/4 of the total triangle ABC. Area of triangle AFE is equals to 1/4 of area of triangle ABC. If you consider any small triangle in this, any small triangle, if you consider triangle CGD or DGC, it is 1/6 of the triangle ABC. Now, again you consider, if you take ABC, here EF I am drawing separately. We know this EF and BC 1:2, their areas will be in the ratio 1:4. This triangle is 1/3. If 4 parts is 1/3 of a triangle, therefore, this one part becomes 1/12 of the triangle. One part becomes 1/12 of a triangle. Therefore, this area becomes area of EFG becomes 1/12 of area of ABC. So, area of EFG becomes 1/12 of ABC. Consider the triangle ABC, and I am drawing all the medians here. Let this point be H. We know G is a centroid and H is a point which intersect AD and EF. We know AG is to GD is equals to 2:1, and we also know AH is to HD is equals to 1:1. Because it is line joining the midpoints, it is in the ratio 1:2, the whole thing. So, AF is to BF is 1:1. In the similar fashion, AE is to EC is also 1:1. Therefore, AH is to HD is also 1:1. So, totally how many parts are there? Here there are 3 parts, here there are 2 parts. So, take a value which is divisible by both 3 and 2. So, I am taking AD is equals to 6. AD is equals to, take it as 6 units. If AD is equals to 6 units, I am dividing AD in the ratio 2:1. Therefore, AG is 2 out of 3 into 6, which is 4. GD is equals to 2 units. In the same manner, AH is equals to 3 units, HD is equals to 3 units. If you take it, AH is 3, GD is equals to 2, remaining is 1. So, finally, we get a ratio AH is to HG is to GD. Is equals to 3 is to 1 is to 2. Here in this chapter, we have seen various kinds of centers of a triangle, and we have gone through the basics of median and how median divides a triangle into different triangles and what are their ratios we have seen. In the next class, we will see more about medians and its properties. Thank you.